we present 3DPR, a single image 3D portrait relighting method with generative priors. Given a monocular input, 3DPR predicts a reflectance basis in the form of one light at a time, or OLAT, images. Our approach preserves the additive nature of light transport. As a result, we can combine these OLATs to render relit portraits. These OLAT images can be combined with any HDR environment map, allowing the input portrait to be relit under any desired lighting condition. Moreover, these OLATs can also be rendered under novel viewpoints, enabling 3D consistent, simultaneous portrait view synthesis and relighting. Motivation. Before we get into the further details of 3DPR, let us first understand why portrait relighting is a relevant and important problem. Human faces are central to a wide variety of applications. For instance, in movies, the lighting on a character's face is often used to convey emotion. Directors actively manipulate lighting and camera movements to enhance the emotional tone and make scenes more dramatic and impactful. And it's not just the movie industry. Faces are critical in many other applications, such as augmented reality and virtual reality, where the lighting from the environment must blend seamlessly with the face for realism of the virtual avatars. On social media, people often post their portraits, and even subtle changes to shadows can enhance the appearance, thus elevating our presence online. Related works. So, having established this is an important problem. Are we the first ones to work on it? Definitely not. In recent times, there have been many excellent works that address simultaneous viewpoint editing and relighting. However, each comes with limitations. For example, PhotoApp relies on a 2D styleGAN to achieve view and lighting control, but it struggles to preserve identity and accurate lighting due to its lack of inherent 3D geometry. Methods such as VORF don't generalize well to unseen subjects. This is due to their limited phase prior and reliance on a slow optimization process. Approaches like McGain and Nelf require multiple input views at test time, limiting their feasibility for monocular applications. More recent methods, such as NERF face lighting, a spherical harmonics-based relighting, and light-to-relight, an environment map-based relighting approach, use 3 DGAN priors and achieve relighting. However, they only produce low-frequency lighting effects, and the relighting quality remains limited. To understand what we mean by accurate light control and high-quality relighting, let's look at some examples. Consider 2 monocular portrait images that we want to relight under colorful indoor lighting conditions, shown here by the reference image. The lighting setup is displayed in the inset. Now, recent methods such as NERF face lighting and light-to-relight completely fail under these lighting conditions due to limitations in their methodology. This failure is primarily because these methods rely only on the EG3D prior for relighting. But these kinds of colorful indoor environments are not represented in EG3D's training distribution, so they simply cannot generalize to such lighting conditions. So we ask the question, what makes a desirable solution? Based on the limitations we've seen, we want a 3D portrait relighting method that generalizes well to unseen subjects, works from monocular input, is 3D consistent during view synthesis, and most importantly, is relightable. The relighting should be high quality and accurate, capturing complex skin-light interactions such as hard shadows, subsurface scattering, specular highlights, and supporting challenging lighting conditions. To summarize, we need a novel 3D face relighting approach that satisfies all these requirements, and also a high-quality face reflectance dataset to support it. Unfortunately, we realize that there is no large-scale, publicly available dataset capable of supporting relighting methods that can handle such complex lighting effects. So, along with our method, we introduce OLAT, a new large-scale lightstage dataset. Our dataset is created by placing subjects in a spherical lightstage dome and capturing them under multiple viewpoints and different facial expressions. We then process the captured images to obtain camera parameters and segmentation masks. Each subject is captured under 331 OLAT lighting conditions from 40 camera viewpoints. We collected data for 139 subjects across diverse demographics, making this the largest public OLAT dataset, focused on detailed face reflectance capture. The dataset includes full head coverage, including the back, at 4K resolution. It spans a wide distribution of age, gender, skin tone, and hairstyle, allowing for the construction of a strong reflectance prior. Method. Now let's see how we combine this light stage-based reflectance prior with the rich generative prior of EG3D. Let's first walk through the training process. Given a portrait image, along with a view direction and light direction, we use a pre-trained encoder to invert the image into EG3D's latent space, extracting high-frequency appearance features. Next, we introduce our OLAT-based reflectance module, which is conditioned on the OLAT light direction. This module models 3D facial reflectance using an efficient triplane representation. It is decoded into a high-frequency feature map and a low-resolution OLAT image. We then combine the reflectance features and appearance features from the inversion stage and feed them into a super-resolution network, which synthesizes the final high-resolution OLAT image. Our ablation studies show that the ESR module plays a critical role. It enables better generalization by preventing the super-resolution network from overfitting to the limited number of light stage subjects. At inference time, 3DPR works like this. Given a portrait image and a desired camera viewpoint, we predict all OLATs for that view. These OLAT images are then linearly combined using the desired environment map to produce the final relit result. Results. Now let's take a look at the results. We'll start by looking closely at OLAT synthesis, which is central to 3DPR. The top row shows ground truth OLAT images of an unseen subject. We present OLATs captured under 4 different lighting directions. Our results, on both light stage subjects and in the wild inputs, closely resemble the reference images, especially in how they preserve lighting direction, hard shadows, and specularities. We also demonstrate the additivity of light transport by summing 2 OLATs and showing that the result matches the ground truth. This clearly shows that 3DPR preserves the linear nature of light transport and achieves precise control, even under point light setups. Also notice, we recover challenging skin light effects such as subsurface scattering, specularities, and self-shadows, highlighted by the rectangles. Next, we show more results on in-the-wild subjects. First, OLAT rendering, and then relit portraits after combining with HDR environment maps under novel viewpoints. Our method closely matches reference relighting under various lighting conditions while preserving expressions and identity across views. 3DPR produces relighting that is both 3D consistent and also consistent across subjects. Evaluation. Now we show qualitative and quantitative comparisons with baseline methods. Both numerically and visually, 3DPR outperforms all existing approaches. It consistently produces relit images that are closest to the ground truth. Next, we explore why explicitly rendering OLATs is superior to directly predicting relit images. To test this, we compare 3DPR with the best performing baselines, NERF face lighting and light to relight, under a progressively sparse lighting setup. We start with a uniform white light, then randomly remove light sources to create sparse lighting conditions. We hypothesize that such sparse lighting conditions lie outside the EG3D training distribution. And indeed, both NERF face lighting and light to relight fail to relight reliably. In contrast, 3DPR handles these conditions well because it renders explicit OLATs and then combines them with the environment map. This flexibility allows it to relight under virtually any lighting condition. Further, we see similar results for colored indoor lighting conditions, and the same holds true for novel view synthesis. Together, these experiments demonstrate that 3DPR strategy, explicitly rendering OLATs and combining them with a generative prior, not only generalizes to unseen subjects, but also provides precise lighting control and robustness to out-of-distribution lighting. Finally, we present important design ablations. Without the ESR module, 3DPR struggles to generalize. The super-resolution network ends up overfitting to the lightstage data, failing to use rich features from the generative branch. As a result, relighting accuracy degrades, especially for unseen in the wild subjects. By introducing the ESR module, we enable feature regularization for the network to better incorporate identity-preserving features and generalize across subjects. Additionally, instead of the popular perceptual loss function, LPIPS, we replace LPIPS with the ID MRF loss, which helps in learning high-fidelity details in HDR space. Our experiments clearly show that these design choices are essential to the performance of 3DPR. To further demonstrate the capabilities of our method, we now present additional video results. We begin with continuous OLAT renderings from a fixed viewpoint. Notice the smooth interpolation of light and shadow across the face, including fine details like moving specular highlights. Next, we demonstrate viewpoint interpolation under 3 fixed lighting directions. Our approach captures view-dependent effects, including subtle in-eye reflections. These results remain consistent across different subjects. We now show relighting of in-the-wild subjects under various environment maps. Our method handles complex lighting variations while preserving facial identity and realism. Lastly, here's a teaser of our OLAT dataset, a high-quality, large-scale data corpus designed to support future research in portrait relighting and human head reflectance modeling. Thank you for watching!